Welcome back to Upgrade to General, a series to help you upgrade your amateur radio license to General class. This episode is Subelement G8 Question Group A, and I'm your host, Ron Call, KE7CR. Normally these episodes are designed to be audio, podcast type episodes where you don't really have to have video. This is one where video might really help. So if you've been listening to the audio only, I'd recommend you watch the video on at least this episode. This episode is about signals and emissions. And to start with, I thought it would be helpful to understand how a radio transmits signals. So this image shown is a block diagram of a radio system. It starts out with an audio frequency source. This could be a microphone. It could be the audio out from a computer. This could be a Morse code key, some source of audio. Then we amplify that audio frequency and then combine it with a frequency from an oscillator. Combining those signals is called mixing or modulating, or another term that's sometimes used is heterodyning. So this image shows two different mixers. So this is what's called a super heterodyne radio, because it mixes in two different stages, or modulates. That's really the magic of how radio signals are going to work, is the mixing. Now, following the mixer, you have a filter to filter out frequencies you don't want and select the ones you do. Amplify that signal again. Mix it another time to get a radio frequency that the wavelengths are short enough that they can easily be transmitted off a physically smaller antenna. And then you have an RF amplifier and then out through a feed line to the antenna. This is an oscilloscope image of a mixed signal or modulated signal. There's a carrier wave, and then superimposed on the carrier wave is a second wave. So you can see here kind of a lower frequency wave and then the higher frequency wave superimposed upon it. That's called mixing or heterodyning or modulating, and that's the magic of what these signals do. So I want to let you see and hear some of the different types of modulation that's used in radio. There's CW or continuous wave. That was the first mode really developed for radio. Then AM, which stands for amplitude modulation, FM or frequency modulation, and PM for phase modulation. This is an example of CW. This is November Romeo 7 Romeo X-ray on lower sideband. Single sideband is a type of amplitude modulation or AM. This is November Romeo 7 Romeo X-ray testing FM. This diagram shows the carrier wave. Now in CW, it stands for continuous wave. It's essentially just a carrier wave at a specific frequency. But the idea was to encode information by turning the carrier wave on and off in a pattern of dots and dashes. That's what the CW means, is continuous wave. So the idea was the wave is always there. It's not really modulating in the sense of combining different radio waves. It's just the carrier wave, and then you turn it on and off. Now, if you modulate by combining waves together, you can get different patterns. This shows an FM wave, which stands for frequency modulation, and the idea is the information is encoded in the frequency of the waves. So some of the waves you'll notice are compressed together in a higher frequency, while other waves are expanded out in a lower frequency. That's what transmits the meaning or the message in the wave. A phase modulated wave is similar to FM. They're really the same kind of wave. It's just, notice the cosine offsets the phase. For FM, this shows that when the modulating wave is at a high peak, the frequency is short waves, high frequency, and at a low modulating wave, the frequency is lower, longer waves. That's shifted off. The phase is just a little different because imagine the cosine of the wave being what's encoded instead of the sine of the wave. So it's the same pattern. You can call that phase modulation. Now this diagram doesn't show amplitude modulation, but with that method, it's the power level that is changing, and that encodes the information. The amplitude modulation, as shown from the video, shows that the power level is fluctuating up and down, and that's what encodes the information in the wave. This is an AM signal. You can see the center carrier frequency and two sidebands, upper and lower sideband. So the bandwidth takes in a much larger bandwidth, 6 kilohertz or so. And this shows a single sideband signal on 20 meters. It'd be upper sideband. You can see the much larger bandwidth, about 3 kilohertz bandwidth for the signal. And this does show that the band is above the carrier frequency, which is indicated by that line. Now, if you tune off, so you can hear how it changes the pitch of the voices as you shift the frequency in single sideband. And this is an FM signal. You can see the huge bandwidth required. I mean, we're going, 200 kilohertz? If you look at the size of the bandwidth there, lots of bandwidth for an FM signal. These are CW signals, Morse code. You can see the narrow bandwidths and how many signals are on at the same time. Each one of these on the waterfall display is CW. And down here you can see the peaks for the signal strengths. Notice each signal is really only 100-150 hertz wide. So that's one of the reasons why CW is so valuable, is you can pack all your power into a narrow bandwidth, and that way your signal can propagate further. And this is showing digital signals, FT8 in particular, on 20 meters at 14.074 megahertz. Notice you can see several strong peaks. Each one of these is a separate station. You can see separate peaks in the zoomed in section of the bandwidth. And this little overlay here shows the typical bandwidth for a single sideband signal. This is upper sideband. And how many digital signals you can fit within the same bandwidth as a typical single sideband signal. This is FT8, and you can see that it's a frequency shift mode. You can see this, say this signal right here, zoomed in, that you can see the frequency shifting back and forth between two different frequencies. So this is FSK, frequency shift keying. Again, you can see two different signals right here. Here's one signal, here's the other signal, and see how they shift back and forth. With that background, now we'll dive into the questions. First question in this section is, how is direct binary FSK modulation generated? Well, binary means two tones. FSK is frequency shift keying, so it means you're going to use two different frequencies to represent the information. So binary means two different tones, and FSK is frequency shift keying. So what you're going to do is change the oscillator's frequency directly by using a digital control signal. So essentially the computer will tell the oscillator what frequency to oscillate at, and you'll go back and forth with those two different frequencies. So that's the answer, changing an oscillator's frequency directly with a digital control signal. The next question, what is the name of the process that changes the phase angle of an RF signal to convey information? Changing the phase angle, that's the phase, so it's phase modulation, or PM. The next question, what's the name of the process that changes the instantaneous frequency of an RF wave to convey information? Well, that's changing the frequency, that's FM, frequency modulation. The next question, what emission is produced by a reactance modulator connected to a transmitter RF amplifier stage? In order to change the phase, you need to change either the capacitive reactance or the inductive reactance. The reactance modulator changes the phase, so it's a phase modulation emission. Next question, what type of modulation varies the instantaneous power level of the RF signal? Power level is changing in an amplitude modulated wave, AM, or amplitude modulation is the answer. The next question, which of the following is characteristic of QPSK31? The two most common kinds of PSK31 transmissions are BPSK31, which is binary phase shift keying 31, and QPSK31, which is quadrature phase shift keying 31. Quadrature phase shift keying transmits 2 bits per phase state and one of 4 phase states during each time period. So 2 bits, 4 possible combinations of 2 different bits. Each of those combinations is assigned a unique phase. So that means twice as many bits will be sent in the same period of time and in the same bandwidth as binary phase shift keying. So the answer choices for this question are, it's sideband sensitive, which it is. The next choice is its encoding provides error correction, and it also does, because there's a total of 4 possible combinations. You can provide some error correction with that. Another choice is its bandwidth is approximately the same as BPSK31. Yes, that's also correct. Both BPSK31 and QPSK31 have a data rate of 31.25 baud and a bandwidth of approximately 60 Hertz. So very narrow bandwidth. So all of these choices are correct. The next question, which of the following phone emissions uses the narrowest bandwidth? The options for phone emissions are AM, single sideband, or FM. Single sideband is really a version of AM. It's just you're suppressing the carrier frequency on one of the sidebands. So in a typical AM signal, like we showed before, it's about a 6 kilohertz wide signal. Single sideband would be half of that, 3 kilohertz wide. FM is even wider bandwidth than that, typically 10 to 15 kilohertz. So the answer is single sideband. The next question, which of the following is an effect of overmodulation? When you overmodulate, you're going to get excessive bandwidth. Sometimes they call that splatter. You're splattering all over the band. Next question, what type of modulation is used by FT8? FT8 is an 8-tone frequency shift keying. So it's FSK uses 8 different tones. You could see in the video I showed before, it looks like the frequency is shifting between different frequencies. There are actually 8 different very close frequencies that it's shifting between. The next question, what is meant by the term flat topping when referring to an amplitude modulated phone signal? Flat topping is when the signal distortion is being caused by excessive drive or speech levels. If you're talking too loud into the microphone and it's amplifying that, you're going to max out the amplitude and it'll flat top those waves and distort the speech level. So the answer, signal distortion caused by excessive drive or speech levels. Next question, what is the modulation envelope of an AM signal? I showed earlier the waveform envelopes for single sideband, FM, and CW on an oscilloscope. The waveform shown in an AM signal is the same as a single sideband signal. It's a waveform created by connecting the peak values of the modulated signal. The next question, what is QPSK modulation? We referred to QPSK earlier. The answer to this question is modulation in which digital data is transmitted using 0, 90, 180, and 270 degrees phase shift to represent pairs of bits. In each transmission, there's 2 bits transmitted that the phases are shifted off from each other by 0, 90, 180, and 270 degrees, 2 of those 4 each time period. The last 2 questions deal with link budgets. Think of a link budget as trying to figure out how much power gets from a transmission to a receiver. So a link budget is the transmitter power plus the antenna gain, which is what increases signal strength, minus any system losses from the receiver antenna feed line and impedance mismatches until you get to the receiver system. So the answer, the sum of transmit power and antenna gains minus system losses as seen at the receiver. And the last question is, what is link margin? Well, the margin is the difference between the received power level and the minimum required signal level at the input to the receiver. In order to receive a signal, you must have some minimum power level. And if you have more than that, that just means the signal is going to be louder. So that's the link margin. Thank you for joining me for this question set. I know this was a lot longer, a lot more information in this question set. Hopefully this helped you understand emissions and signals better. And look forward to seeing you in the next question set. 73, this is KE7CR.